What's going on, smart people? Bringing you another episode of Tensor Calculus for Physics Majors. In the last video, we talked about transformations of two-index tensors. And a lot of times it's convenient to project a two-index tensor onto some coordinate system and work with its matrix representation. But sometimes that matrix representation will or will not be nice to work with. And by nice to work with, I mean its matrix may or may not be diagonal. A diagonal matrix is one whose off-diagonal components are zero. Now, if the matrix representation is not diagonal, the question is then, is it that way because of some intrinsic, complicated nature of the tensor itself? Or did you just choose the wrong basis to represent it by? And as it turns out, a symmetric, real, second-rank tensor can always be diagonalized. So for this video, we're going to pick on the inertia tensor, which is a symmetric, real tensor, and I'm going to show you how to diagonalize it, and then we'll make some final comments before we get into the metric tensor next video. Let's kick things off by considering angular momentum. We're going to end up projecting everything onto some xyz basis. Using Dirac notation, we know that the angular momentum is equal to the inertia tensor, which I will have as this double arrow, acting on angular velocity. And if we consider some tires rotating about some axle where it's pointing in the z direction, so we have something like this. Here's our angular velocity that is pointing in the z direction. In an ideal situation, meaning like your tires are well balanced, the angular momentum will be pointing in the same direction as the angular velocity. But this is not always the case. If you've ever driven a car where the tires are unbalanced, you'll feel it shaking quite a bit because the angular momentum is not pointing in the same direction as the angular velocity. But let's go ahead and expand out this representation. What this is saying is Lx, Ly, Lz is equal to, this is going to take a second, this inertia tensor in matrix representation times omega. And I just said that omega is in the z direction, so we'll notate that by 0, 0, omega z. If we carry out this matrix multiplication, we get that Lx is equal to, we get 0, 0, Ixz omega z, omega sub z, let's call it that, or I guess we'll do that, whatever. Right now we're not worried about what's contravariant or covariant indices. Okay, Ly, Iyz omega z, and Lz is equal to Izz omega z. So here's our expression for angular momentum components. We want angular momentum to strictly be pointing in the same direction as omega, which should be in the z direction. But it can't just be pointing in the z direction if we have these other components of angular momentum. We know omega z, we're assuming, is not 0, which means we need a way of proving that Ixz and Iyz are. And we can do that by considering the geometry of the object we're calculating these components for. So we're dealing with tires. Tires, if we're assuming a uniform continuous mass distribution, are basically cylinders, right? So they have some cylindrical symmetry that we can exploit. So let's write down cylindrical coordinates real quick. X is equal to r cosine phi, y is equal to r sine phi, z equals z. And our measure, dv, is equal to r dr d phi dz. Cool. We defined our component of the inertia tensor earlier to be Iij is equal to the integral of r squared Kronecker delta Ij minus xi xj summed over all of the masses. Okay? Now let's take a look at xz. And by symmetry, we're also looking at zx because the inertia tensor is a symmetric tensor. Ixz, well, that's just equal to, well, delta ij. If I does not equal j, this is just 0, so that's 0. It's going to be minus, and I'm going to write a triple integral, xz dm. Substituting in our values for cylindrical coordinates, and dm is just rho dv, where rho is the mass density, and this is equal to triple integral of r squared cosine phi z dr d phi dz. Now the thing that makes all of these components simplify quite a bit is the fact that we're integrating over this angle, over the angle of the tires, which is going from 0 to 2 pi. So theta, or phi, is going from 0 to 2 pi. The only difference between Ixz and Iyz is the fact that instead of using a cosine in yz, we'll be using a sine. But since we're integrating from 0 to 2 pi anyways, both of these integrals go to 0. So this is 0, and similarly, Iyz is equal to 0 because we're integrating sine from 0 to 2 pi. By symmetry, Izy equals 0, and so does Izx. So the last thing that we're going to have to take care of, so we just showed that this is 0, this is 0, this is 0, and this is 0. That still leaves yx and xy. They don't show up explicitly in the angular momentum, but we'll show real quick that those are also going to be 0. So I'm going to erase this real quick. Okay. If we want to find, say, Ixy, that's again equal to minus the integral xy dm minus the integral of r cubed now times cosine phi sine phi dr d phi dz. This is also 0 because we have an odd function times an even function integrating from 0 to 2 pi. So this is also going to contribute 0. So at the end of the day, our representation of the inertia tensor simplifies to Ixx, 0, 0, 0, Iyy, 0, 0, 0, Izz. What this means is we've conveniently chosen a basis where one of our basis vectors points along the axis of rotation, a principal axis of rotation, and everything aligns perfectly such that we chose the right set of basis vectors that diagonalizes our matrix. But we won't always be so lucky. So next, we're going to get into an example where we don't have a diagonal matrix, and I'll show you how to diagonalize it. So if we don't have a uniform mass distribution, there's no reason to think we can exploit this symmetry and think that our tensor will be diagonal. So the mechanic will diagonalize the tensor by changing the mass distribution itself and adding weights. We, on the other hand, have the luxury of choosing a different basis. Now we were kind of lucky with that last example. We already had a set of basis vectors that diagonalized our inertia tensor for us. But now let's purposefully screw things up a little bit. We'll start with an inertia tensor that is not diagonal and change our basis to one that does diagonalize the matrix. Turns out that a more natural basis to represent the tensors in such that it diagonalizes them is the basis such that the basis vectors are just the eigenvectors of the tensor itself. Now, we're going to assume that our inertia tensor, represented in some basis, Iij, so coordinates are xi's. Well, this is just the matrix element I, j. And like I said, we're going to assume that in this basis, the tensor is not diagonal. The goal is then to find some new coordinates, that's an m, some new coordinates we'll call x alpha, where alpha is our set of new basis vectors that are also the eigenvectors of I, such that I alpha beta is equal to this matrix element, alpha I beta, and we want it to be diagonal, and that's going to turn out to be some eigenvalue times Kronecker delta alpha beta. Now this isn't the same eigenvalue multiplied by each row. This is going to be the eigenvalue of the beta eigenvector. Right there, the Kronecker delta is just 1 0, 0, 0, 1, 0, 0, 0, 1. So like lambda 1 times this, lambda 2 times this, lambda 3 times this. So this lambda is not just one number times the Kronecker delta, it's the set of eigenvalues. Great, so we've established that we want to find the eigenvectors of this tensor, and it will diagonalize our tensor for us. The next step is how to find the eigenvectors. Well, it's the same as any other way. Let's write the matrix version of this equation. I, acting on our eigenfunction, or eigenvector, is equal to its eigenvalue times the eigenvector. Subtracting this over and factoring out the common factor of this eigenvector, we get I, this arrow's annoying to draw, minus lambda, identity matrix, times this, is equal to 0. Why am I writing this identity matrix? Well, we have a tensor of rank 2 here. We can't subtract a scalar from a tensor. That doesn't really make sense, so we have to make sure that it's the same rank. Now we're looking good to start finding these eigenvectors. One kind of condition that we have to impose is that the determinant of this quantity here has to equal 0. So the determinant of I minus lambda is equal to 0. The reason for this is if it's not, then we can assume that this matrix can be inverted. And if it's inverted, yeah, we'll have a unique solution for beta, but if we multiply by the inverse, then the inverse times this would just give us the 0 vector again, and we would get beta equals 0 no matter what this is. And that is, well, that's not very interesting. So we want to impose this not being invertible by saying that its determinant will equal 0. Then solving this will let us find the eigenvalues of our matrix here, and then after that we'll be in good shape to actually find the eigenvectors. Requiring that the determinant equals 0, well, yeah, we won't necessarily have the trivial solution anymore, but we also lose uniqueness. But we'll be able to recover uniqueness again by imposing that our eigenvectors be orthonormal. So we'll end up normalizing them, and we'll get a unique solution again. Let's actually do an example. We're going to pick on the inertia tensor one more time. The components of the inertia tensor should have units of mass times distance squared. And to keep me from having to write ma squared a bunch of times, I'm going to introduce some parameter, I think that's an eta, is equal to ma squared. That way I don't have to write this all those times. So let's introduce some inertia tensor that won't be diagonal, and then we'll diagonalize it. So we'll let I equal, I'm going to write eta times 2 minus 1, 0, minus 1, 2, 0, 0, 0, 4. This is different from the one given in the tensor calculus book that I've been using, and I'm using this one because in that book they kind of just give you the eigenvalues and say, hey, we calculated it. And they do that because if you actually go through the calculation like I did, you end up getting factors of like 1 over 432, which is extremely disgusting. So I changed the problem a little bit to make the algebra a bit nicer. I still made it so that the eigenvalues will give us real and positive eigenvalues, which is what you should expect for the inertia tensor to begin with. Now, if we want to find the eigenvalues, we need to do the determinant of I, and I'm going to lose the arrow, you get the idea that this is the inertia tensor, minus lambda times the identity. Okay, so this is equal to eta times, well actually no, let's keep the eta in there. We'll do determinant of 2 eta minus lambda minus eta 0 minus eta 2 eta minus lambda 0 0 0 4 eta minus lambda. Okay, and this should equal 0. And this is going to give us a characteristic equation that will let us solve for our eigenvalues, and then we will use those eigenvalues to get our eigenfunctions, or our eigenvectors, sorry. If you're already familiar with finding the determinant of a 3x3 matrix, you can go ahead and skip to this video, but I wanted to be careful just in case some people forgot how to do that. So let's go ahead and do that. The first way, or the first step of finding this determinant is we want to find it associated with this coordinate, so we write that it is 2 eta minus lambda times, block off the column, block off the row, and it's this determinant. The second part is going to give us 0, so this is going to be 2 eta minus lambda 4 eta minus lambda. Then we're going over a column, so it's minus eta. Block off the column, block off the row, and we get minus eta times 4 eta minus lambda. And again, the other term is just going to be 0 times 0. And we already have a 0 here, so that's just going to zero out the next term. So it's plus 0 equals 0. And now we just want to solve this characteristic equation for lambda. So let's distribute everything out, and we will get, let's see here. So this is going to be a 4 eta squared minus 4 eta lambda plus lambda squared times 4 eta minus lambda. Minus, minus, minus. So this is minus eta squared 4 eta minus lambda equals 0. We have a common factor of 4 eta minus lambda, so let's go ahead and factor that out. And we get times this. We're going to have a 4 eta squared minus an eta squared, so that's 3 eta squared minus 4 eta lambda plus lambda squared is equal to 0. Let's go ahead and solve this for our first eigenvalue. We get that 4 eta minus lambda equals 0. Called lambda 1 is equal to 4 eta. Cool, one eigenvalue down. Now let's do the same thing here. We get 3 eta squared minus, actually I'm going to represent it in decreasing order, so let's do lambda squared minus 4 eta lambda plus 3 eta squared equals 0. And this should actually factor. This could give us lambda, let's see, minus 3 eta, and then lambda minus 1 eta. Let's go ahead and multiply this out just to make sure. So that's lambda squared minus eta minus 3 eta plus 3 eta squared. So that does give us it. So that tells us that our other eigenvalues are lambda equal to 3 eta and lambda equal to eta. Perfect. Now that we have our eigenvalues, let's go ahead and find these eigenvectors. This took me so much longer when I tried to go through the algebra that was actually given in the book. Awesome, so we have our 3 eigenvalues. We will have 3 associated eigenvectors, because remember, we're looking for I to be acting on some eigenvector to give us that associated eigenvalue times that eigenvector again. And we'll write out distinct names for our eigenvectors. We'll let them equal, let's call one rho, one will be sigma, and let's let another one equal gamma. So these are going to be our 3 eigenvectors. So the first one that we want to do is we want to find I acting on a rho should give us, and let's make it associated with lambda 1. So let's do lambda 1 times rho. Let's get started. So I, again, we know that that's eta 2 minus 1, 0 minus 1, 2, 0, 0, 0, 4, acting on rho, and we'll let its components be rho 1, rho 2, rho 3, rho 1, rho 2, rho 3, is equal to the eigenvalue 1, which is going to be 4 eta. That's, there we go, times our eigenvector again. So rho 1, rho 2, rho 3. Right off the bat, we see that the etas just cancel. Again, assuming that the mass is not 0 and that a is not 0. So if we multiply this out, the first component of our eigenvector is going to be 2 rho 1 minus rho 1, rho 2, is equal to 4 rho 1. So we just did matrix multiplication and then took it as equated our coefficients here. And then let etas cancel. Okay, and then we can subtract over this 2 rho 1, and we get that minus rho 2 is equal to 2 rho 1. Solving for rho 1, we get rho 1 is equal to minus 1/2 rho 2. Great. Let's do the other equation. So this is, now we're looking for rho 2. So this is going to be minus 1. So minus rho 1 plus 2 rho 2 plus 0 rho 3 is equal to rho 2, 4 rho 2. Okay, let's subtract over the rho 2's, and we get minus rho 1 is equal to 2 rho 2, or let's just multiply by minus 1. Now we get rho 1 is equal to minus 2 times rho 2. So we're having conflicting things here. We're saying rho 1 is equal to 1/2 basically of rho 2, and it's equal to twice. The only way for this to be satisfied is if rho 1 or rho 2 is equal to 0, which would make rho 1 equal to 0. Okay? Now, for the final equation, we get 0, 0, 4 rho 3 is equal to 4 rho 3. 4 rho 3. So we just get rho 3 equals rho 3. It's not very helpful, but we can fix this. We can make this unique. You see why I said that this gives us something that might not be unique at first, but we can make it unique by imposing that our vector be orthogonalized. So in other words, rho should equal 1. Let's go ahead and do that. This is our first and our second. These are our first and second and our third. So we get 0, 0, rho 3 times 0, 0, rho 3 is equal to 1. And that just tells us that rho 3 is equal to 1. Great. So now we have a unique eigenvector. Let's go ahead and write that up here. So rho is equal to 0, 0, 1. 1 down, 2 to go. I'm going to erase this, and I'm sure you'll see a pattern here. We're basically doing the same thing 3 times. So now let's do sigma and have that be associated with lambda 2. So we'll make that sigma 1, sigma 2, and sigma 3. Lambda 2 is 3 eta. Sigma 1, sigma 2, sigma 3. Again, etas cancel, and we can multiply it out component by component. We get that 2 sigma 1 minus sigma 2 is equal to 3 sigma 1. Subtract this over, we get that minus sigma 2 is equal to sigma 1. Okay, so that's one thing, that's one condition that we have. Let's do it for the second row now. Minus sigma 1 plus 2 sigma 2 is equal to 3 sigma 2. Let's subtract this over, and we get minus sigma 1 is equal to sigma 2. So we get the same thing here. Okay, final equation, we get 4 sigma 3 is equal to 3 sigma 3. Again, this can only be satisfied if sigma 3 is 0. So sigma 3 equals 0. Since we know that sigma 1 is just minus sigma 2, we can fix these two by, again, imposing orthogonality, or orthonormality, I should say. So let's go ahead and normalize it. So we'll do sigma is equal to, now we don't know what the first two are, we just know that they're opposites of each other. So let's just have them in terms of sigma 1. So we'll have sigma 1, we know sigma 2 is just minus sigma 1, and then we have 0. Sigma 1 minus sigma 1 and 0. Sigma 1 squared plus sigma 1 squared is equal to 1. So 2 sigma 1 squared is equal to 1. So sigma 1 is equal to 1 over root 2. Well, that also defines sigma 2 is equal to minus 1 over root 2. Now we can collect all of these terms, and right here, and create our second eigenvector. So sigma is equal to 1 over root 2, 1 minus 1, and 0. On to the final one. Last step is to finally find the third eigenvector. I've already expressed it in here. Let's go through the exact same motions. So writing out this matrix multiplication, you guessed it, 2 gamma 1 minus gamma 2 is equal to gamma 1. Subtracting this over and adding that over, we get that gamma 1 equals gamma 2. Next equation, minus gamma 1 plus 2 gamma 2 is equal to gamma 2. Again, gamma 1 equals gamma 2. Super helpful second equation. Last one, 4 gamma 3 is equal to gamma 3. So that tells us that gamma 3 has to equal 0. Then we fix these constants again by just normalizing our eigenfunctions, eigenvectors, and we get, so gamma equals 1 equals, let's call it gamma 1, 0, gamma 1, 0, gamma 1 squared, 2 gamma 1 squared is equal to 1. So gamma 1 is equal to 1 over root 2, which also tells us that gamma 2 is equal to 1 over root 2. Okay, so now we can write our final eigenvector to be gamma equal to 1 over root 2, 1, 1, 0. Great. The last step that we have to do is we have to just create a matrix out of these eigenvectors. So we'll call this matrix U. So we'll put it up here. Let U, I'll erase this as well. Let U equal a matrix consisting where each row is an eigenvector. So we will have 0, 0, 1. 1 over root 2, 1 over root 2, minus 1 over root 2, and 0, 1 over root 2, 1 over root 2, and 0 again. I'm actually going to factor out the 1 over root 2 because I'd rather deal with root 2's than 1 over root 2's. This is equal to 1 over root 2, 0, 1, 1, 0, minus 1, 1, root 2, 0, 0. The last thing that we want to do is we have to recall how these tensors transform, how these matrices transform. We can transform a matrix, any matrix like this. T prime is equal to the transformation using our unitary matrix, which is what these are representing, times our unprimed U. This is transposed. I have an entire video proving this transformation property here, which I'll link in the description. I know a lot of this I've already covered in multiple videos, but I think it'll be nice to have it all in one, except for this one. This would add another 15-20 minutes to the video. So we need to transform our inertia tensor by multiplying it by this matrix that's formed by its eigenvectors and the transpose of that matrix. So let's find what this is. So that tells us that U transpose, again, it's going to be the 1 over root 2 out front. Rows become columns. So 0, 1, 1, 0, minus 1, 1, and root 2, 0, 0. So here's our U transposed. Now let's find out, once and for all, if we act on our inertia tensor here, with these matrices here, do we get a diagonal matrix? Let's see. So U transpose is, well, multiplying 1 over root 2 times 1 over root 2, so that's just going to contribute a 1/2 total. Transpose 0, 1, 1, 0, minus 1, 1, and root 2, 0, 0. Sandwiched in between all of this is going to be our inertia tensor, which is going to be eta times all this. Let's go ahead and pop the eta out front here. 2 minus 1, 0, minus 1, 2, 0, 0, 0, 4, times the untransposed 1, 0, 1, 1, 0, minus 1, 1, root 2, 0, 0. And let's do our matrix multiplication. I'm going to go ahead and erase, let's see, I guess up here is as good a spot as any to erase. Okay, so this is eta over 2. This means over here. Zero, 1, 1, 0, minus 1, 1, root 2, 0, 0, times this matrix multiplication. So we've got 0, 0, 0, 2, 1, 0, which is 3, and 2, minus 1, 0, which is 1. Next row, 0, 0, 0, minus 1, minus 2, 0. So minus 1 minus 2 is minus 3. And then minus 1 plus 2 plus 0. So we've got a 1 again. Final row, we've got 0, 0, 4 root 2, 0, 0, 0, and 0, 0, 0. Final matrix multiplication, this is equal to eta over 2, 0, 0, 4 root 2 times root 2, so that's going to give us an 8. Then we've got 0, 0, 0, this is 0, 0, 0, 0, okay, 0, 0, 0, 1 minus 3, 3 plus 3, 0, so that's a 6. 1 minus 1 plus 0, which is 0. 0, 0, 0. I said 0 so many times it's starting to not sound like a word anymore. 1 or 3 minus 3 plus 0, so it's a 0. 1 plus 1, so that's a 2. Giving our final representation, so our, let's call it I, what was the index I was giving it? Alpha, beta, I guess? Or let's just call it I prime since we're not just representing the elements, is equal to 1/2. So we've got 4 over 2, so that's 4, or 8 over, wow. So we've got 8 over 2 times eta, so that's 4 eta. Okay, 0, 0, 0, 3 eta, 0, and 0, 0, eta. So not only does constructing the eigenvectors diagonalize the matrix, but the fact that we normalize them makes it so that the diagonal elements are just the eigenvalues of those associated eigenvectors. So let's recap what we just did. This was the inertia tensor that we started with, and this is our diagonalized inertia tensor. But what does this mean physically? Well, this is corresponding to the inertia tensor for some object rotating about some axes. The fact that we diagonalized it means, from the beginning, we said that our angular momentum is equal to the inertia tensor times the angular velocity. Expressing it this way means that if we have a rotation about one of these basis vectors, about one of those axes, the angular momentum is guaranteed to also be in that direction. So if we have angular velocity in the rho direction exclusively, so will the angular momentum. So that's what makes it so powerful to be able to diagonalize our tensors in this way. Being able to diagonalize tensors is going to play a bigger role later on, which I thought is why it deserves its own video today, even though I've covered it in bits and pieces in other videos. The last thing that I want to talk about is changing gears a little bit, because I want to take the definition of transformations of two-index tensors themselves and show an alternative way of thinking about them. So if we were to have some tensor in a prime frame, ij, we know now that that transforms as dx prime I, say dxk, some other index, dx prime j, dxn, tkn. So we have our tensor, transformation coefficients, and the component in the transformed frame. But think about for a second the way that just vectors transform. If we were to define, say, the I prime component, so a transformed vector component, we know that that's equal to dx prime I to dxk, ak. Similarly, we can have another vector that we'll call b prime, let's call it j. So these are components. I keep calling them vectors. These are components of vectors. So this is equal to dx prime j, dx, let's call it n. Let's not reuse our indices. bn. And if we multiply these two vector components together, we get a prime I, b prime j is equal to dx prime I, dxk, dx prime j, dxn, ak, bn. And that looks an awful lot like this definition of how a two-index tensor transforms. In fact, it's exactly the same. And we can define this tkn to be the product of these vector components, ak, bn. And at this point, it shouldn't look too surprising to express it this way, because we know if we have, say, a component of the inertia tensor, iij, this is the integral of r squared delta ij minus xi xj integrated over all the mass. Here we know that the Kronecker delta is a two-index tensor, but we don't know explicitly that the product of two vector components makes one as well, and now we do, by taking the definition of how vectors transform and multiplying them together. More specifically, what we're doing is we're saying that we can create a tensor by taking what's known as the outer product of two vectors. And this is also going to play a bigger role in the future videos. In the next video, we're finally going to delve into the metric tensor. I'm looking forward to that. Hope you guys found this video helpful. Let me know in the comments section if you'd like to see maybe some exercises from this book worked out in a future video, and I'll see you guys there.